Hello, my name is Eileen Solomon, and today we're going to do a review of first-order differential equation solving techniques. We're going to go through the methods one at a time and just do one example of each type of problem. All right, so our first problem that's on the screen is separable differential equations. We recognize a differential equation is separable by looking for factors of x times factors of y times dx plus factors of x times factors of y times dy equals 0, which is the form that we have on the screen. Cap f of x times cap g of y times dx plus lowercase f of x times g of y times dy equals 0. If our differential equation is not written in this form, it might be given as dy dx form, then we try to separate the variables to be in this form, and then we divide as necessary to solve our equation. So looking at our first example, we have the differential equation y squared plus 1 quantity times dx equal y times secant square x times dy. This is separable because the factors of y are separate from the factors of x already. So all we need to do is get the x's with the dx and get the y with the dy. All right, so we're going to use the screen here to separate our variables, and we're going to divide both sides of the equation by the factor y squared plus 1 to get the y's with the dy. And of course, the differential has to be in the numerator to be able to integrate. And that will get rid of that factor. But of course here we need to get rid of the secant square x factor and move it over here with the dx. So we divide by the product of secant square x times y squared plus 1, and that will then eliminate secant square x from the right-hand side, and all that's left is a function of x times dx equals a function of x times dy. That's what we want. Now, to make it a little bit easier to integrate the left-hand side, because that's the next step, is to integrate both sides of the differential equation, we're going to write the reciprocal of secant square x in the numerator. So that now becomes cosine square x times dx equals y over y squared plus 1 times dy. And the next step, of course, is to try to integrate both sides of this differential equation. Okay, so cosine square x was the reciprocal of secant square x because 1 over secant x is cosine x. And now to integrate even powers of sine or cosine, remember we have to use the power reducing identity. So the left-hand side needs to be rewritten as 1 plus the cosine of double the angle divided by 2 times dx. The right-hand side is almost the way we want it. All we really need is a 2y in the numerator. So to get that 2 times y, we're going to have to multiply by 2 and divide by 2. That'll give us the du over u that we could integrate. So now on the left side, we're going to factor out the 1/2 factor that's in the denominator here. And then we're going to be left integrating the numerator. Split it up in this example, just so you can see how that works. Okay, and then on the right, that's equal to 1/2 times the natural log, absolute value of y squared plus 1, which is the same as y squared plus 1. And one of these integrals has to contain our arbitrary constant of integration. Okay, so I'm just going to put it on the right side. It's just as easy to do it there. All right, so now let's finish the integral on the left. So the integral of 1 dx is x. The integral of cosine 2x is sine 2x divided by 2. I've already got my arbitrary constant on the right, and we just copy what we had for the integral on the right expression. Now that's a correct answer. It's just not as pretty as we might make it. So to simplify it a little bit, we could multiply both sides by 2 and get rid of these fractions. And then, you know, we could multiply by 2 again if we wanted to get rid of the denominator under the sine 2x. So 2x plus sine 2x equals 2 times the natural log of y squared plus 1 plus 2c, which is just a different arbitrary constant. So you could leave it like that. It's not really a big deal. There are other ways that that could be written. We could certainly move the constant to the left and get rid of ln if we wanted to. We'd have to use our properties of logs to do that. But I wouldn't have a problem with your leaving an answer like this just because you don't have any logarithm terms on the left side of the differential equation that would make it easy to simplify this. It would be nice to get rid of ln, but it's not required because the exponential expression on the left would be kind of ugly. So I wouldn't have a problem with that. If you wanted to leave the problem that way, that would be just fine. So separable differential equations, if we look back at our technique, our technique, we started out with factored coefficient of dx, factored coefficient of dy. So we didn't have a lot of factoring we had to do. But sometimes that will be required. And then we were able to just divide both sides by variable products in such a way that we were able to get x's times dx and y's times dy. That's what we have to be able to separate it so that we can then use integration to finish the problem. Once we integrate, then we try to simplify our answer as much as we can by just doing basic algebra like multiplying both sides of the equation by the LCD, which is what we did in that particular problem. Okay, all right, let's move on to our second method. All right, so the second type of differential equation we want to talk about are those that are linear. A linear differential equation typically is one that has a function of x times dy dx plus a function of x times y equal a function of x. Now, in this particular setup, it's already put in standard form with a coefficient of 1 in front of the dy dx term. That has to be done first. If it's not given that way, you've got to rewrite it in this standard form, dy dx plus some function of x, we're calling p of x, times y equal a function of x. And when you have a standard form linear differential equation that's linear in y, you're going to need to find next the integrating factor, and that's what we call the mu of x factor here. That is the integrating factor, and once we get that, then we can multiply both sides of the differential equation by the integrating factor, and the left side will magically turn into the derivative of the product of mu of x times y. And then, of course, the next step would just be to integrate to get rid of the derivative. So it works very nicely, but you have to have your differential equation in the correct form before you're able to do that. All right, so let's look at the example on the screen. X squared plus 4 quantity times dy equal the quantity 2x minus 8xy times dx. All right, so the first thing we want to do is divide both sides by dx because we need to have the dy dx form. So let's take care of that. Okay, now it's still not the way we want it because we need a y term. So we're just going to add this term to both sides of the differential equation. So now x squared plus 4 times dy dx plus 8xy equal 2x, okay, which is linear. We've got a function of x times dy dx plus a function of x times y equal a function of x, but it's not in standard form because our initial coefficient of dy dx is not 1. So one more step ought to do it. We're going to divide both sides by x squared plus 4. Okay, and that now gives us our coefficient of 1 that we want. So if we want to rewrite this just to make it prettier to work with, dy over dx plus our function of x, 8x over over x squared plus 4 times y equal our q of x, or function of x over here on the right. All right, so at that point, we've got it in standard form. Now we're ready to find our integrating factors. So let's come over here and work with finding mu of x. So we want to take e and raise it to the integral of this p of x factor, 8x over x squared plus 4. And we're going to integrate with respect to that variable x, of course, if we want a function of x. All right, now to do this integral, it's helpful to kind of rewrite the 8x as 4 times 2x. So that's all I'm going to do here. Rewrite 8 as 4 times 2, pull in the 4 on the outside. And the reason, of course, we want to do that is we need du over u. And the derivative of the denominator is 2x, not 8x. So now that we've got that, this is e raised to the 4 times the integral of du over u, which is ln absolute value of u. But you remember, when you're finding an integrating factor, we're not looking for all of the integrals. We're looking for one. One integrating factor will do it for us. All right, so this coefficient now, we're going to bring up here and make it an exponent. So the e raised to the natural log of something, the e and the ln cancel each other out because they're inverse functions, and all we have left is the argument x squared plus 4 raised to the 4th. Okay? All right, let's kind of box that off so it won't be in our way. And so now our next step is to use that integrating factor on our standard form differential equation. So we're going to multiply both sides of the differential equation by that integrating factor. Don't skip this step, because if there's something wrong with your integrating factor, you can catch it right here. So x squared plus 4 to the 4th divided by x squared plus 4 is going to leave us x squared plus 4 to the 3rd. And this factor of x squared plus 4 will also cancel out, so we'll end up with 2x times x squared plus 4 to the 3rd, which works very nicely for us. Okay. All right, now if we've done the correct integrating factor, this entire left-hand side now should be the derivative with respect to x of the integrating factor, which we already know, times the dependent variable y. And you're not changing the right-hand side, you're just rewriting the left side. Now, you should always check this step. So check to make sure that that works. If you go back and take the derivative of that product, is it equal to the left-hand side that you started out with? Well, first factor times the derivative of the second, that part's already taken care of in the first term here. But second factor times the derivative of the first, we need to make sure that that is the derivative of x squared plus 4 to the 4th. And of course, the derivative of u to a power is the power times the inside function to the power minus 1 times the derivative of the inside. 4 times x squared plus 4 to the 3rd times the derivative of x squared plus 4, which is 2x. And so that is exactly what we've got up above. So that means our integrating factor is right. If that doesn't check, you need to erase those two lines and go back on the right to your integrating factor and redo it. Find your mistake, because that's the only way that this would not work. All right, so now that we've got a derivative with respect to x of something equals something, I can get rid of the derivative with respect to x by integrating both sides. And so all that's left is x squared plus 4 to the 4th times y equal the integral with respect to x of 2x times x squared plus 4 to the 3rd. And because we had a derivative with respect to x here, we have to integrate with respect to x on both sides. So that's where the dx comes from. All right, fortunately, that's an easy integral, because if we did a u substitution, let u equal x squared plus 4, then we've got u cubed times the du. This part of it would be the du if, we had x squared plus 4. So I don't really have to do a formal u substitution on that one because I can see the u to a power times du. So this is simply going to be x squared plus 4 to the 4th divided by 4. And again, every time we integrate, we need an arbitrary constant of integration, except when we're looking for the integrating factor, because there we're not looking for all of the solutions. We're just looking for one integrating factor. All right, so at that point, let's change our colors here. At this point, we want to isolate y. So to get y by itself, we're going to divide both sides of the equation by x squared plus 4 to the 4th. And so that's going to give us 1/4 for the first term plus a constant divided by x squared plus 4 to the 4th. Now that's perfectly fine if you wanted to leave your answer like that. If you want to have a single fraction, that's not a lot more work. It's totally up to you how you want to simplify. But that is an explicit solution, so there'd be nothing wrong with leaving our answer in this form. All right, so if we summarize our technique again, we start out by rewriting our differential equation in standard form, which in this problem required that we divide by dx, and then we had to divide both sides by the coefficient of dy dx, which was x squared plus 4. Once we got our differential equation in standard form here, then we were ready to find our integrating factor mu of x over here on the right. Once we found our integrating factor and we simplified it, then we had to multiply both sides of our differential equation by the integrating factor and rewrite that sum as the derivative of a product of the integrating factor times the dependent variable y. And of course, we won't always have x and y, so you got to keep that in mind. The y is the dependent variable in this differential equation. And then just integrate both sides to get rid of the derivative and simplify by solving for y. Every linear differential equation can be written as an explicit solution like we have in this problem. Okay? So the y equals is a good form. All right, next type of differential equation we want to consider are those that are exact. Remember, an exact differential equation should be possible to rewrite it as some m of xy relation times dx plus some n of x and y relation times dy equals 0. And all that means is your coefficients of dx and dy can have a mixture of x's and y's in them. But it's not exact unless this is true. The partial derivative of m with respect to y, notice y is not this variable, it's the opposite variable, okay, has to equal the partial derivative of n with respect to x. So these are partial derivatives, and then the solution requires partial integrals, okay? So, once we know that it's an exact differential equation, which we always have to check, and if it's written in the form m dx plus n dy equals 0, you might as well, unless it's obviously separable. I mean, if you can see right away that you can factor the coefficient of dx and the coefficient of dy, then fine, work it as a separable differential equation, and you won't have to worry about this. But otherwise, you should go ahead and do the simplifying. All right, so to integrate, we're going to simply find the solution function f of xy equals c by integrating m with respect to x, and that's got to be a partial integral because m is going to usually have both x and y in it, and the partial integral of n with respect to y will also be a mixture of variables, and you want to integrate with respect to y. These two can then be compared. So you're going to have functions of x, you'll have terms that have both x and y, you'll have terms that have y, and then you might have a leftover function of y or function of x because of the partial integrals and the way the partial derivatives work. So you're going to compare what you get from these two answers to find all the terms that have to be in your f of xy expression. All right, now let's look at example 3. All right, so this problem requires that, let me move this to the top just so, that's a little bit too far, just so we'll have room to work. All right, so now the differential equation is the quantity, 6x plus 1, quantity closed, times y squared times dy dx, plus 3x squared plus 2y cubed equals 0. It's not quite in the form that we want, because we'd like to see something times dy plus something times dx equals 0, or doesn't matter what order those terms are in. So I'm going to multiply both sides by dx just to get it closer to the form that we want. Zero times anything, of course, is still going to be 0. And the only difference in this differential equation and the regular n dx plus n dy, of course, is the order of the terms. So if that bothers you, then you can reorder them. Make sure that the coefficients are the same. So now we've got our m times dx plus our n times dy, okay? So that's going to give us our starting point for figuring this out. We're going to check, since we've got n dx plus n dy, we're going to check to see if it is exact. All right, so you're going to do partial derivatives. And the coefficient of m is x here, dx. So we're going to integrate with respect to the other, excuse me, I said integrate, differentiate. We're going to differentiate partial derivative with respect to the other variable y. All right, so that's going to be taking the m expression here, and derivative with respect to y means you're treating x as a constant and only using the derivative rules on the y expressions. So the derivative of 3x squared with respect to y is 0 because it's being treated as a constant. The derivative of 2y cubed with respect to y is 6y squared. Okay, so that works. Now let's take the derivative of n with respect to its opposite variable. Remember that one was y, so we use the other variable x, and the partial derivative with respect to x, you're treating y as a constant and using the derivative rules on x, okay? So you've got this product, but as far as the product goes, since you're actually taking the derivative with respect to x, you're kind of treating the y squared as if it's a constant multiple of that variable factor. And so the 6x plus 1 has a derivative of 6, but then that's multiplied times the, quote, constant factor of y squared here. So these are equal to each other. And since they are, we know that the differential equation, sure enough, is exact. Don't forget to check that before you use the technique of integrating to find your function of xy. Because if you don't, then it's not going to work. All right, so to get the f of xy function, we're going to do the partial integral of m, which is 3x squared plus 2y cubed. And it's partial integral with respect to x, so we use that kind of curvy delta symbol to stand for partial integral. And since we're integrating with respect to x here, we're treating y as if it's a constant. And so when we integrate x terms, it's regular integration rules. The integral of 3x squared, for example, is going to be 3x cubed divided by 3, which is just x cubed. And then the integral of 2y cubed with respect to x, since we're treating that as a constant, you know, the integral of a constant dx is a constant times x. So we're going to get plus 2 times x times y cubed. Now, usually we would put a plus c when we do an integration problem, but this is a partial integral. And so you have to remember that any function of y would have a partial derivative with respect to x of 0. So this could be any leftover function of y, and we don't know what that is. It could be a constant. It could be an actual expression that's got y in it. That's why we have to do both the integral of m with respect to x, and we have to also do the integral of n, which we're about to do, with respect to y. So n was this product of 6x plus 1 times y squared, and we want to do a partial integral with respect to y. Okay? All right, so when you're doing a partial integral with respect to y, you're kind of treating x as a constant. And so 6x plus 1 here would be like a constant in our expression. And we could always factor out a constant, you know, as a typical rule of integration. So that constant factor times y to the third divided by y. I said y to the third divided by y. I meant y to the third divided by 3, of course. And the leftover function would be some function of x this time. So we might write h of x. Now, the only thing about that is hard to compare with it written in this form. So let's go ahead and simplify this first fraction. Let's write it as 2 terms. So 6x times y cubed over 3 becomes 2x times y cubed. And then 1 times y cubed over 3 is just y cubed over 3. Okay? So now we're going to compare these expressions. Okay? All right, so we have an x cubed term by itself here. And we also have an h of x here. So those have to match up. And then we have the 2xy cubed term, so we know that's in both of them. And then the extra g of y factor right here also has to be included in our f of xy. All right, so now to write our solution, which we would call the general solution. Let me go back to the blue. All right, we can write f of xy, which has to have all 3 of those terms, 2xy to the third, plus the x, went up too far, x cubed term, plus the y cubed over 3 term, equals c. And we have to allow for the arbitrary constant because we don't know that g of y or h of x didn't still include an arbitrary constant. So we just set f of xy equal to c once we found our function of x, our function of y, and our function of both x and y. And so that's the answer. That satisfies the equation. Now, of course, you can simplify it other ways. You could multiply both sides by 3 if you wanted to clear out the fractions. There are lots of prettier answers that are possible. All right, so let's review our technique. So the first thing we had to do was get it in m dy plus n, or m dx plus n dy equals 0 form. And all this algebra was just to put it in that form. Once we've rewritten it here in m dx plus n dy form, then we can check with our partial derivatives to see that it is an exact differential equation. Once we verify that it's exact, we know this technique of finding the partial integral of m with respect to x and comparing it with the partial derivative of n with respect to y will work for us to find all of the terms that have to be in our f of xy equals c solution. And that's what we're doing here in the last step. Okay, so it's not a real hard technique. So we've done separable, we've done linear, and now we've done exact. And those are the 3 most easy techniques for first order differential equations. Now we're going into our substitution methods. Okay, so the last 3 types of problems are those that require a change of variables, some substitution technique. So we're going to look at Bernoulli differential equations first. Bernoulli was a famous mathematician, and the name Bernoulli is applied to any differential equation that is almost linear except for a power of y on the right-hand side. So if it looks like it's a linear differential equation because you have a function of x times dy dx plus a function of x times y equal a function of x times, and then you have this extra factor of y to a power. And it could be a positive, negative power, it doesn't matter. That would still be a Bernoulli differential equation. Anything other than n equals 0, of course, because if n was equal to 0, y to the 0 be a constant, we wouldn't have any problem because that would just, be a function of x and it would be linear. All right, so to solve this, you typically want to put your differential equation in standard form the way this one is written, with our leading coefficient of 1. And then the next thing you want to do is divide both sides by y to the n, which of course is the same as multiplying by y to the negative n. And you want to simplify. And what ends up happening is the middle term is going to have some power of y in it. And whatever that power is will be y to the 1 minus n. Because here you have a y to the 1, and you're going to divide it by the y to the n. So you're going to end up in the middle with y to the 1 minus n. Once you do that, then you'll have to find dv dx. And you want to try to rewrite the whole problem in terms of v. Okay? All right, let's look at our example. So in this differential equation, we do have a function of x, x times dy dx, minus the quantity 1 plus x, quantity times y, equal x times y squared. Now, it's not in standard form because of our leading coefficient of x. So I'm going to take care of that problem first. I'm going to divide both sides of the equation by x. You don't have to pretty this up a lot yet. Okay? So now you can see it's linear as far as the left-hand side is concerned, but now I've got this extra factor of y on the right. Now, the fact that there's no x's on the right should not bother us because a constant like 1 is a perfectly good function of x. So that still is linear except for the power of y squared on the right. So the next thing we're going to do is multiply both sides by y to the negative 2 to get rid of the problem on the right. And of course, y times y to the negative 2 becomes y to the negative 1. And then all we have left on the right is 1, because we're basically dividing both sides of the equation by y squared. All right, now it's this power of y that you want to represent v. Okay? So the rule was to let v equal y to the 1 minus n power. So if we look at that, isn't that what we have here in the middle? Y to the negative 1. And we need to find dv dx. So the next step is to differentiate both sides with respect to x. That gives you negative y to the negative 2 times dy dx. And if you'll notice, all we would need in our first term to get dv dx is to multiply both sides by negative 1. So let's use a factor of negative 1, and we're just going to multiply both sides by negative 1. Okay? So whatever the missing coefficient is in your dv dx, you want to multiply both sides of your differential equation by that missing coefficient. All right, so now we're going to rewrite. So the left side is dv dx. Now the middle term is positive, and we've got this 1 plus x over x times what we're letting represent v equal negative 1. Okay. All right, so now we've got a perfectly good linear differential equation in the dependent variable v. So now what we want to do is find our integrating factor. So every Bernoulli differential equation, when substitution is done correctly, will become a linear differential equation in terms of the new variable. Whether you use v, u, w, it doesn't matter what you use for your new variable. All right, so we're going to look for our integrating factor mu x. E raised to the integral of 1 plus x over x. I'm going to go ahead and separate those fractions. because that'll make it much easier to do the integration. So this expression is 1 plus x over x. This part of it, remember, is our p of x over here. All right, so this becomes e to the ln x plus x power. Okay, and when you have a sum on your exponents, you can always rewrite that as a product using the same base. So e to the first term times e to the second term, because that's how our rules of exponents work. When we multiply powers on the same base, we keep the same base and we add the exponents. And the first factor, of course, can be simplified. So this integrating factor now is x times e to the x. Okay? So we need to multiply both sides of this differential equation by the integrating factor. Okay, so that's going to give us x e to the x times dv dx. The x will cancel in this factor and leave us e to the x times 1 plus x times v equal negative x e to the x because of the negative 1 that we have on the right. Okay? All right, so now if we've done this correctly, the left side should now be the derivative with respect to x of the integrating factor times the dependent variable. The right-hand side does not change in this step. So that's what we need to check. We need to make sure that that's right. Because if we've made a mistake with our integrating factor, we would know that was not true if we didn't do the check. And this part of it, certainly, the first term is going to be right because first factor times the derivative of the second, well, that's going to be all right. It's really this part as the derivative of this that we need to check. So let's just do that part of our derivative check over here. Derivative with respect to x of the product of x e to the x. Well, it's first factor times the derivative of e to the x, the second factor, plus the second factor times the derivative of the first, which is just 1. And if we factor out the e to the x, sure enough, it is e to the x times x plus 1, which is what we had right here. So, yes, that does check, and we can go on with our differential equation. All right, so now to get rid of the derivative, we integrate both sides with respect to x. And so that gives us x e to the x times v equal the integral of negative x e to the x dx. Well, unfortunately, that's one of those challenging integrals that requires integration by parts. All right, so we have to kind of off to the side or on scratch paper, we need to actually do that integration. Okay, so that's going to require our technique. Let me change colors here. So we're going to let u be negative x. Sorry, I'm putting marks all over the page with my fingers. Try this again. All right, so the u equals the polynomial part, the negative x factor, and dv being not the same dv we're talking about in the other variable. This is just for this integration, e to the x times dx. All right, so my du is the derivative times dx, negative dx, and v is the integral, which is e to the x. And so that integral then, the integral of u dv, remember from integration by parts, is u times v minus the integral of v times du. So in this problem, it's negative x e to the x minus the integral of e to the x times negative dx, which becomes negative x e to the x plus the integral of e to the x, which is e to the x. And plus c, of course, but we'll put that over here when we integrate it. All right, now let's go back to our problem. So we had copy what we had on the left, write our result from the integration to be negative x e to the x plus e to the x plus our arbitrary constant of integration. Okay. And the last step is to isolate v. So you're going to divide both sides by x e to the x. Which can be simplified, but I would wait to do any simplifying because you don't know what's going to happen until you go back to the original variable. So at that point, you want to go back. What did v stand for? In our original substitution, v was y to the negative 1. Okay, so now down here, you got to go back to that variable. And of course, if we've got, the reciprocal of y equals a fraction, then to get y, all we have to do is take the reciprocal of both sides, which is then flip this fraction. And that's the answer. Not very pretty here, but that's supposed to be an x. And again, and I always like for my students to circle their final answers so I know what it is they want me to grade. And so there's really not a whole lot you can do with that. I mean, you could divide numerator and denominator by e to the x, but that's going to give you a c e to the negative x in the last term of the denominator. So I don't know that that's really that much prettier than what we have right now. All right, so reviewing the technique. The Bernoulli differential equations become linear in a new variable, and I'm always trying to use the new variable v. So if you do the correct technique and the correct substitution, it should become linear in the new variable v. So our steps involved on the example, putting it in standard form by getting our leading coefficient of 1, which we did in that step. And then the next thing that we did was divide by y squared to get it in, get rid of the problem on the right that keeps it from being linear. So dividing by y squared. And then we saw when we did our substitution, our change of variable, letting v represent the y power that's in the middle, y to the 1 minus n is the rule, and taking the derivative of both sides with respect to x, we saw that we needed a -1 coefficient. And so the next step was to multiply by that missing constant of -1 on both sides of the equation to get the dv/dx. So we rewrote the differential equation in terms of v in this step. And then the next thing to do was recognize that once you've rewritten and simplified, that the left side is the derivative of the product of the integrating factor times the dependent variable v in this case. And then we had to integrate. This particular problem required integration by parts to find the integral here, which we did on the right. Right, we went over here and did our integration by parts. And then we isolate the variable v. So in every linear differential equation, it's possible to get an explicit solution for v. It's not always pretty to get an easy expression for y, but this one was, because v stood for y to the -1. All we had to do was leave that as a single fraction, and then we could flip both sides of that equation, take the reciprocal of both sides. Now, one word of warning, because sometimes I'll see students do this on the tests. If you had had y to the -1 equals, let's say, x over 2 plus 3 over x plus c, you could not take the reciprocal of all the terms. Some new c is what that would be. That is not true. You cannot take reciprocal of terms. You have to have a single fraction and then take the reciprocal of that entire fraction. So don't make that mistake of trying to simplify it that way. You want to leave your differential equation as y to the power equal the single fraction, then do whatever you need to do to get y by itself. All right, let's look at our next type of differential equation. And this is one that is almost separable. Okay? So the key, I mean, almost separable would require factoring, so that's not really true. But we're going to turn the homogeneous differential equations into separable differential equations in terms of a new variable. So when would I recognize that I had a first order homogeneous differential equation? Well, it requires that the coefficient of dx and the coefficient of dy all have terms that have exactly the same degree. Or another way, sometimes we define homogeneous as it is possible to rewrite the differential equation in the form dy dx equals some function of y over x or some function of x over y. Sometimes we want to do the substitution in terms of x over y instead of y over x. So basically, our technique is to rewrite with a change of variables. Okay, so if we have a function of y over x, or they all have the same degree in this form with m dx plus n dy equals 0, then usually letting v represent that y over x will work. Okay, and so when we do that substitution and solve for y, it gives us let y equal vx. And what we're going to do is just replace all the y's with vx, and then we're going to replace the dy in the differential equation with v dx plus x dv. And of course, that just comes from the product rule for differentials. All right, let me get some room to work here so we can have some extra room to actually work this problem out. All right, so clearly in example 5, the coefficient of dx and the coefficient of dy all have the same degree. So the quantity 3x minus 5y times dx plus the quantity x plus y, all multiplied times dy, equals 0. Same degree terms. That's what's required for being homogeneous. So this is homogeneous of degree 1, or of order 1, sometimes we'll call it. All right, so our substitution is to let v equal y over x, which would give us y gets replaced with v times x, and dy equal v dx plus x dv. These are all related substitutions if you're letting v replace the y divided by x. All right, so now in our differential equation, we're just going to copy the x terms. But every time we have to replace y, we're going to replace y with vx. So this next term becomes minus 5 vx, all multiplied times dx, plus the quantity, keep the x, replace the y, and replace the dy. Okay, trying to get rid of all the y's, including the differential. Now, the next step is to collect all the dx terms and then collect all the dv terms. So we already have some dx terms over here we want to include. These are dx terms. But this product of this expression times this term will also be dx terms. So we want to include those. So x times v will be there, or v times x, no matter, of course, what order we put those in. And then this product of vx times v becomes x v squared, all multiplied times dx. Now to get the dv terms, I'm going to take this one times the dv expression in that binomial. So that's going to give us x squared plus vx squared times dv equals 0. Now, if you prefer, you can FOIL out that binomial product, x plus vx times v dx plus x dv. I just find this is faster for me because I know my next step would be collect the dx terms and collect the dv terms. All right, so now let's see if there's any like terms that we can simplify. On the left, these two terms are like terms, so I can combine those to get negative 4. xv, vx doesn't really matter, plus x v squared times dx. and then I'm really just copying this side, but I'm going to go ahead and factor the x squared out of those terms. And now I want to factor the x out of all the terms in the coefficient of dx. Remember, homogeneous differential equations are supposed to become separable. And if they are separable, you should be able to separate the variables by factoring when you get to that step. And that's what we've done. Let me get a little bit more room for us to work here. All right, so now we're ready to get the x's with the dx's and the v's with the dd. So we're going to have to do some division. Divided, of course, we're dividing the 0 as well, but we get the same thing. So we want to get the x squared here with the dx terms. And so we divide both sides by x squared. And then we want to get rid of the v's, so we're going to divide by this expression. And that'll give us an equivalent differential equation. Remember, sometimes we lose possible trivial solutions when we do this dividing by a variable expression, but ordinarily it's not really a big deal. We don't really care that we're losing x equals 0 when we divide by x here. Now, you know, in some cases the trivial solutions can be important, but they're not really a big deal for this problem. I'm going to write these terms in descending power order. Just thinking about trying to make it easier for me to integrate in the next step. All right, so once we had separated the variables, then we are ready to integrate both sides. So that now, once we get the integrals done, will be the majority of the difficult steps in the problem, right? So this integral is easy. This integral in the middle is not quite as obvious as we would like, but fortunately for us, that denominator is factorable, okay? So if I kind of come over here to the side, and let's do the rewriting of the fraction 1 plus v over v minus 3 times v minus 1. That's the factorable form of that denominator. I know a partial fraction decomposition will work here. So I want to find that a over v minus 3 plus a b over v minus 1 with constants a and b that will make that the same. Okay, so I'm going to multiply both sides by the original denominator. That gives my basic equation, 1 plus v equal the fraction. The first fraction times the LCD leaves me a times v minus 1. The second fraction times the original denominator gives me b times v minus 3. And by substituting convenient values of v, like v equal 1 or v equal 3, I can find the values of a and b. So when I substitute v equal 1, I get on the left side 2. The a times 0 zeroes out, so all that's left on the right is v times 1 minus 3, which is negative 2. And when we divide both sides by negative 2, we find the value of b. When we substitute v equal 3, on the left side we get a 4, and the first product, a times 3 minus 1, is a times 2. The b factor, of course, again zeroes out, so all that's left is 2a equal 4, or a equal 4 divided by 2, which is 2. All right, so now this integral is the integral of a over v minus 3 plus b over v minus 1. So I still have to integrate that, but at least we're well on our way. And of course, the integral of 0 is c or ln c. In this case, we might want to change it to an ln. In fact, I think I'm going to go ahead and do that, because each of these fractions in the middle is going to be an ln, which is just another constant. Ln of a number is a number. All right, so now integrating the rest, we get plus 2 ln absolute value v minus 3 minus ln absolute value v minus 1 equals ln absolute value c. Rewrite the left-hand side as a single natural log. Okay, So remember, this coefficient has to become an exponent so that you can use the properties of logarithms correctly. And so this is going to be ln plus ln is the natural log of a product. And then minus ln becomes a factor of the denominator. You have to divide. All right, so once we have a single logarithm equals a single logarithm with the same base, we could exponentiate both sides of the equation and eventually get that x times v minus 3 quantity squared divided by v minus 1 has to equal the absolute value c. And of course, to remove the absolute value, all we need to do is plus or minus the opposite side. So if I do plus or minus c, that's just a different constant. So let me write it c1 just to indicate it may not be the same c, but some constant is going to be there. All right, now at this point, usually you want to figure out what v represented. So you go back to your original substitution, and in our problem, v stood for y divided by x. So when I come in here and I want to simplify this mess, I'm going to have to replace the v with y over x. And there's several ways that you can simplify from here, but I would not accept an answer that's left in the form of a complex fraction like this one is. So there's a couple of things that you can do. One of the easiest would be multiply numerator and denominator by x, because that will eliminate the x in the denominator. So let's just change that. So that'll give us x squared times, and I'm going to go ahead and square this binomial now. So when I square the first term of y over x minus 3, I get y squared over x squared. And then I double the product of the two terms and get 6y over x. And then I square the last term. And when I multiply the x times the quantity y over x minus 1, of course, all I get is y minus x. I didn't write that very well. Some arbitrary constant. And of course, now in the next step, I just distribute the x squared through in the numerator. So I get y squared minus 6xy plus 9x squared, all divided by y minus x equals c1. And you could leave your answer like that, or you could multiply both sides of the equation by the denominator. This is not going to be an easy problem to write as a y equals. In fact, most of the time when you're doing a type of differential equation that's homogeneous, you will not be able to get an explicit solution that's y equals some function of x. You're probably going to have to leave it as a relation, which is what we have here. All right, so let's look back over our steps, make sure you've got the technique down. All right, so first we check to see that it is homogeneous. We did that by checking the degree of each term in our coefficient of dx and dy. These are all the same degree. Because of that, we know, yes, it's homogeneous. And so the appropriate substitution is to let v equal y divided by x, which means y equal v times x, dy equal v dx plus x dv. And the next step was just to do that substitution. We replace all the y's with v times x, and we replace the dy with the expression v dx plus x dv. Then we collected all of our like terms, all the dx terms, and all the dv terms, and then we factored, we simplified and factored to rewrite it in a separable form. And then we have to integrate whatever is left. So we integrate every term on both sides of the differential equation. This particular fraction was not a du over u, this one in the middle. So because it's not a du over u, I had to use partial fraction decomposition over here to be able to rewrite that single fraction as the difference of 2 over v minus 3 minus 1 over v minus 1. So partial fraction decomposition I showed on the right. Once we did that, then we could integrate each term on both sides, and we wanted to get a single logarithm so that we could easily undo the logarithm using exponentiation, or if ln u equals ln v, then u has to equal v. We know that's true. So that's another way of thinking this through. And then all you want to do is simplify. So you rewrite v equal y over x and do the algebra to simplify your complex fraction. All right, so our last method is not real common. In fact, you probably will find few examples of this particular linear substitution. Okay, so what we have in this type of problem is specifically dy dx equals some clear function of a constant times x plus a constant times y plus a constant. And of course, a, b, and c are just in for numbers here. They're not variables in the problem. So usually you'll have grouping symbols. Occasionally you might have to rewrite the right-hand side, the dy dx equals, so that you can see the common linear expression x plus by plus c. So the goal is whatever that linear expression x plus by plus c turns out to be, you're going to let that be replaced with a new variable like v, and then you're going to find dv dx using regular differentiation rules, differentiating both sides with respect to x, and then you're going to solve that for dy. Okay, so you're going to solve for dy. Once you get all that, you'll be able to substitute. All right, let's look at the example, which example 6 is clearly not in dy dx equal form, so it's not real obvious right now what we need to do. But that's pretty easy to get, because if we divide both sides by the linear expression, now we've got dy dx, and I'm going to write it that way. So that linear expression, 2x plus y plus 1, that's what we're going to let v represent. So after you choose what your new variable is going to be, you want to find the derivative of both sides with respect to x, which is 2, the derivative of 2x with respect to x, plus 1 times dy dx. Of course, the derivative of the constant 1 is 0. So that's all I have, but remember, I'm trying to solve for dy dx. So that dy dx now needs to be replaced with dv dx minus 2. Okay, so those substitutions are what we're going to use in this expression. All right, so dy dx is replaced with dv dx minus 2. And on the right, all I have is 1 over v. Okay? All right, so, you kind of have to look at each differential equation separately at that point, figuring out what it is you want to do as far as your technique, because there's no guarantee that this is going to become linear or that it's going to become separable. You just have to look at each problem separately. So I'm going to isolate the dv over dx term by adding 2 to both sides. And because I want this to be a single fraction, I'm going to add 2 in the form of, excuse me, that's not correct, 2v over v. Okay. All right. So now I can get a single fraction on the right, 2v plus 1 or 1 plus 2v, doesn't matter, over v. And that is a separable differential equation. So if I multiply both sides by dx to get rid of the dx here, and then I multiply both sides by the reciprocal of the fraction on the right, I'm going to get v dv over 2v plus 1 equal dx. So now that I've got the variables separated, these with dv, no x's with the dx, but a constant's perfectly good. Now I'm ready to integrate both sides. Okay, so unfortunately the fraction v over 2v plus 1 has the same degree in the numerator and the denominator, and so there's no way it could be a du over u. It's just not possible. So this is a problem where we actually have to do the division. So you're going to have to divide v by 2v plus 1, which is not pretty, but it's what's required. So there's a couple other tricks that you can do. For example, if I would factor out the 2 from the denominator, then that would leave me v plus 1/2, which is kind of weird, but the right-hand side is easy to integrate. Let's go ahead and do that one. All right, so then all I'd have to do really to get the du over u is add and subtract 1/2 to the numerator term. So we could use that little trick. Because we're just adding nothing, adding 0. All right, so now we can separate the two fractions. This is sometimes a little bit faster than dividing, but dividing is just fine. So v plus 1/2 over v plus 1/2 becomes 1, and then minus 1/2 over v plus 1/2. That will be, of course, 1/2 times ln. So it's kind of up to you how you want to rewrite that, and we have to integrate that with respect to v. So now the integral of the first term is v. The integral of the second fraction is 1/2, because we have to pull that numerator out, times the natural log absolute value of the denominator. Okay. And at that point, you probably forgot what your substitution was. Let's get rid of the 1/2 on the outside and the 1/2 here by multiplying both sides of this differential equation by 4. We'll just pretty it up a little bit. So 4 times 1/2 is 2, and when we distribute the 2, we get 2v minus the natural log of v plus 1/2 equal 4x plus 4c, which is just another different constant of integration. All right, and when we go back and we look at our original substitution, v represented 2x plus y plus 1. So that's what you're going to substitute now down here at the end of the problem. All right. 2x. I already forgot what it was, so let me look it up for a minute. Right, so it was 2x plus y plus 1. And of course, the plus 1 plus 1/2 becomes a 3/2. And that would be a perfectly acceptable answer as far as I'm concerned. We don't have, much simplifying that's possible on that thing, but that would be okay. Or you could kind of combine some like terms. Let me show you one other optional way of simplifying. If you multiplied the 2 through, you get 4x plus 2y plus 2. Not really anything you can do here. We already added the constants together. So you can see that you could subtract the 4x from both sides, and that'll drop out. You could kind of lose the plus 2 because of the c1 on the right. You don't really need that constant on both sides of the equation. So really, you could simplify this with 2y minus the natural log absolute value of 2x plus y plus 3/2 equal c. That's a little bit better, but I really don't care. Any equivalent answer I would accept. Now, I wouldn't want you to leave a whole lot of terms with ln in it, but there's only one ln in this problem. And even if you isolated the natural log, you're still going to have y's on both sides of the differential equation. So your answer is not going to get a whole lot prettier than that. But anything that was equivalent would be accepted. All right, so hopefully this brief review of first-order differential equations techniques will help you in your first unit of ordinary differential equations. For today, that's all we are going to cover. So I appreciate your attendance to this video, and feel free to contact Mrs. Solomon if you have any questions.